Hello everyone. So today we'll be going through ideal gas equation and we'll be dealing with absolute temperature. So we have thermometers we use to measure temperature. So there are some thermometers which have a glass case, and this is the glass case, and there's this liquid inside. So those are called liquid in glass thermometers. They show, so for temperature T, different liquid in glass thermometers, they show different readings because the liquid used, because not all liquids have the same expansion property. They have different expansion properties. So for example, there's thermometers uses mercury, which we found commonly, and this thermometer uses alcohol. Then for a temperature rise, alcohol will expand more, that will show a higher temperature, and mercury will expand lowly and therefore show a lower reading. So that's one of the drawbacks of the liquid in glass thermometers. And now there are thermometers that use gas, so what we call constant volume gas thermometers. So thermometers that use gas, they give the same readings regardless of which gas is used. They give the same readings. They give the same readings because all gases at low densities exhibit the same expansion behavior. So in constant volume gas thermometers, we use low density gases. We use low density gases. So the behavior of a given, as written here, the behavior of a given quantity of a gas depends on its pressure. The behavior of a given quantity of gas depends on its pressure, its volume, and temperature. Pressure, volume, and temperature is what the variables describing a gas: pressure, volume, and temperature, where this temperature is taken in Kelvin. That's the absolute temperature scale, is taken in Kelvin, absolute temperature scale. So so when temperature so when the temperature of a constant volume of a gas, low density gas, is held constant, temperature is held constant, then the pressure and volume of a quantity, that's mass, the pressure and volume of a mass of a gas are related as PV equals constant. And don't confuse with this constant and this constant, these are different constants. So when temperature is held constant, the product of pressure and volume of a low density gas is constant. So this is known as Boyle's law. This is known as Sir Boyle's law, after Sir Robert Boyle, the English chemist who discovered it. Now this was when temperature was constant. Now what happens held when we hold volume? Sorry, when we hold pressure, the pressure as constant. So when pressure of a low density gas is held constant, then V over T, the volume of the gas over its temperature, equals constant. This is known as Charles law. After the French chemist Sir Jacques Charles, who discovered it. So Charles law and Boyle's law, these are the fundamental laws in the starting of science. Low density gases obey these laws. We can say low density gases obey these laws, which may and these and Boyle's law and Charles law may be combined in a single relationship. Charles law may be combined in a single relationship, and what we call that's what we call the ideal gas law. That's what we call the ideal gas law. Now, since um, Boyle's law says PV equals constant when temperature is constant, and Charles law says V over T equals constant when pressure is constant. So it implies PV over T equals constant, and this is the ideal gas law. This is the ideal gas law means that's valid for an ideal gas, and an ideal gas is a low density gas. It can be written in a more general form. The ideal gas law can be written in a more general form that applies not just to a given quantity of a single low density gas, but to any quantity of any low density gas. But to any quantity of any dilute gas means low density gas. Dilute gas that means a low density gas. Dilute gas means a low density gas. There's this keyword dilute. Dilute gas meaning low density gas. So when the ideal gas law is is written in a more general form, it becomes the ideal gas equation. PV over T, which equals constant, equals nu R, where R is the universal gas constant, and nu, that's mu actually. Mu is number of moles. R has a value of 8.31 joule per mole per Kelvin. So this is the ideal gas equation, valid for any quantity of any dilute gas. So nu r are constant, PV by T equals constant, so PV is directly proportional to temperature. As temperature rises, the product of pressure and volume also rises. So this relationship allows a gas to be used to measure temperature in a constant volume gas thermometer. In a constant volume gas thermometer, measure temperature. PV is proportional to T. So holding the volume of a gas constant. The means P is proportional to T when volume is held constant. So P is proportional to T. Thus, temperature is read in terms of pressure. In a constant with a constant volume gas thermometer, temperature is read in terms of pressure. So a plot of pressure. So this is a plot of pressure versus temperature. So pressure is on the y-axis, temperature on the x-axis. So that's what we call pressure versus temperature. So pressure versus temperature. As we know, P is proportional to T, holding the volume constant. So that means clearly P over T equals constant, and P over T is the slope. P over T is, if this is, so P over T is clearly a constant. So means P over T is a constant. Just a minute. So if we just draw a straight line right here and measure this angle, this angle will be equal to P, this angle will be equal to P over T, which P over T, theta, theta, theta will be equal to P over T, which will be the slope of this line. P over T is the slope of this line. P over T is the slope of this line. P over T is the slope of this line. So this, the plot of pressure versus temperature is a straight line. But as so this clearly indicates that the pressure can become zero at this point. Pressure can become zero at this point, at this temperature. But as the temperature is so lowered, the the gas actually changes its state. It transforms in a liquid and then solid. So measurements on real gases deviate from the values predicted by the ideal gas low at low temperature, because the gas doesn't continue to be a gas. So but the relations, we can see this relationship, the pressure versus temperature, P over T, this relationship is linear, means P over T equals constant. This relationship is linear over a large temperature range, and this is the large temperature range. This is the large temperature range. This is the large temperature range. So, and this relationship is linear, and the pressure might become zero, might reach zero with decreasing temperature if the gas continued to be a gas. So so to infer this temperature, we extrapolate we extra we extrapolate this plot and see that you can see this dotted line, this what we call extrapolating. So extrapolating, and this temperature is found to be minus 273.16 degrees Celsius, and is designated as absolute zero. So absolute zero is the foundation, is the starting point, of the Kelvin scale, of the Kelvin temperature scale, which is the absolute temperature scale, is absolute temperature scale, so which is named after the British scientist Lord Kelvin. So on this scale, the Kelvin scale, also known as absolute temperature scale, minus 273.15 degrees Celsius is taken as 0 point, that is 0 Kelvin, minus 273.15 Kelvin. We can see here. And the relationship to And the relationship to go from Celsius scale to Kelvin scale, because we usually measure temperature in Celsius scale and we need actually in Kelvin scale. So this 273 add 273.15 in 270 add 273.15 in the temperature in Celsius to get the temperature in Kelvin. So this is the relationship. So, well, try this. If the temperature in Celsius is minus 273.15, so added to 273.15 equals 0. So 0 Kelvin is minus 273.15 degrees Celsius. Thanks for watching.